Hello everyone and welcome. In this video we are going to discuss how to design URL shortening service. Let's first understand what URL shortening service is. Okay, so it is a service that converts long URLs into shorter aliases. Okay, what does this mean? You give it a long URL like this one and it will convert it into a short URL like this. Okay, how does it help? Short URLs are convenient to use. They take shorter storage space when stored in database or elsewhere, and they are less prone to errors while being typed. Okay, so that's why short URLs are more convenient than longer ones. What are the functional requirements of this service? Very first, as the name suggests, it should be able to convert long URL into the short ones. Then given a converted short URL, it should be able to convert or redirect the short URL request into the longer URL. Okay. Third, the client should be able to generate custom URLs. So if the client wants to give some specific name on his own, he should be able to do this. Then the converted URL should expire on its own by default after some time. Okay, and if the user wants, he should be able to delete the URLs as well. Okay, the very last requirement is that these URLs should not be sequential. So it should not be like ABC123, ABC124, ABC125. These are sequential URLs. So these kind of URLs are prone to attacks. So the short URLs should not be sequential. So these are the functional requirements of our system. Let's look at the non-functional requirements. Okay. Very first is the low latency. What is meant by low latency? The link redirection should not take very long time. Okay, so basically conversion or redirection from short URL to long URL should not take a lot of time. Okay, if it takes a lot of time, it makes the user experience go bad. Next is high availability. So availability is extremely important in this case. Why is it so? It is because even a small amount of downtime will lead to redirection failure. The short URL would not be able to convert to the longer URL. So having a short URL, the purpose of having short URL fails here. Okay, so we cannot have downtime at all. Third is the scalability. The number of URLs that are going to be converted and the number of redirection requests are going to be in millions. So the system should be scalable. Like as the demand goes up, the system should be able to scale itself. These are the non-functional requirements. Now let's discuss what database should we use. In order to know what database to use, we should understand what kind of data we need to store. Okay, so we need to store the mapping between the original URL and the shortened URL. Okay, next we may need to store user ID. Why? Because we need to know which user gave this particular shortening request. That's it. We don't need anything else apart from this. So these are the requirements. Okay, now we need to understand one thing. The amount of requests that our system gets for converting long URL into shorter one is going to be very less in comparison to the amount of requests we get for redirection. What I mean to say is the number of requests for conversion are going to be less, very less in comparison to the number of requests we get for redirection. That means that our system is going to have less write requests and more read requests. So our system is going to be read heavy. Number of read requests are going to be way more in comparison to the write requests. Okay, that is one thing. Then there is not much relationship between data apart from mapping, and we may need to know which user gave the conversion request. So that's pretty much it. other than that we don't have relationship between the data. Okay, that means our system is not going to have very complex queries or joins. Okay, another characteristic of our storage. Then the third thing, because we need no latency, the read and write request should be fast at scale. So these are the characteristics of the data that we are going to store. Now let's discuss what DB among between SQL and NoSQL would be the best for our case. So from the characteristics we discussed, NoSQL is the clear choice because the read and write request in SQL take significantly more time in comparison to NoSQL when we are talking about scale. Okay, so we'll be choosing NoSQL database. Okay, now we have many choices in NoSQL database also, right? We have MongoDB, we have Cassandra, we have DynamoDB. Which one to choose? To understand this, we need to know the architecture and how these databases handle read and write requests. So we'll begin with MongoDB first. So MongoDB, yeah, MongoDB follows leader follower architecture. Okay, so it has multiple replicas, and amongst the multiple replicas there would be one leader and others would be followers. So there is a single leader in each partition. Okay, now in this case, how does the write operation happen? How does it execute the write operation? The write operation has to go through the primary node or the leader node, and having a primary node avoids split brain scenarios and write conflicts. What does that mean? In case of concurrent writes from multiple clients, the primary serializes these concurrent writes and then executes them in consistent and atomic way. Okay, so writes are not going so multiple writes are not going to multiple nodes. All the writes are going to go to a single primary node only, and even if the writes are concurrent writes, the primary or the leader node would serialize these writes. So it executes them in consistent and atomic way. Okay. Then the read operation. Read operation can happen through any node. It can be replica also. It can be the primary or leader node also. And even if the primary or primary replica crashes, the system is available for read intensive tasks. So reading availability is guaranteed. So that is how write operation happens. Now let's see the Cassandra or DynamoDB. So Cassandra or DynamoDB follows peer-to-peer architecture. So they are leaderless databases. What does that mean? How would write operation happen in them? A write or read operation can happen through any node. You can, if you want to write something, you can go to any node and write on it. If you want to read something, you can go to any node and read from it. Now because of this, since there is no leader, write operations provide weak atomicity in case of concurrent writes, apparently, because there is no leader to serialize these writes. Okay, and during read operation, the client can fetch data from multiple replicas. Okay, now if all the data that is fetched from multiple replicas, if that data is same, then you can simply return the data to the client. But if the data fetched from multiple replicas is not same, then the system needs to know what all replicas have stale data. Okay, and then provide them with the latest data. So this whole process of giving the updated data to the replicas, it is called as read repair. Now read repair adds latency to the read operation, which is not suitable for our system. Okay, so Cassandra and DynamoDB needs read repairs, which is adding latency. So that is one problem with Cassandra and DynamoDB. There is another thing that we need to consider. Cassandra inherently provides more availability in comparison to MongoDB. Why? because of peer-to-peer architecture. Uh, it can handle both read and write request in case if some node goes down, other node would still be up, right? So it provides more availability. Now it may seem like MongoDB provides a little bit less availability. Why? Because if the primary node goes down, uh, the leader election algorithm will kick in. Okay. Now the leader election algorithm takes some time to select a new leader, and post that the right operations can be done. But while the leader is being elected, uh, our system will not be available for the right operations. So for this small amount of time our system will not be available. uh, so from this discussion it may seem like MongoDB is making our system less available, but that is not true. The small amount of unavailability is fine. Why? Because the time taken to select a leader is going to be very less than the time uh, elapsed between URL generation and the first time the URL is being used. So it is fine. I mean, we can allow small time of unavailability. Okay. So availability of system is not actually being affected by this small unavailability. Let's see how does the high level design of system look like. What can our system get as input? It can get a long URL that needs to be converted into a short URL. It can get a shortened URL that needs to be redirected or converted into a long URL. Or it may get a URL that needs to be deleted. Okay. So we will primarily need three services: a shortening service, a redirection service, and a deletion service. Okay. So whatever URL we get, it goes through a load balancer or an API gateway. Okay. API gateway will route the request to the appropriate service. Each of these services connected to the database, and ahead of database we keep cache for faster lookup. Okay. Now let's see how does shortening service look. So we discussed that the shortening service will get a long URL and it needs to be converted into a short one, but we need to ensure that the long URL has not already been converted. So as soon as we get long URL, the system checks if the long URL has already been converted. So it checks if the long URL exists in the system or not. If it exists, it simply returns the corresponding short URL back to the client. If it doesn't exist, then we'll need to generate a short URL. Now how do we generate a short URL? We need two components for that. First is we need a unique ID generator or sequencer. Okay. We need a unique ID generator or sequencer. What does this do? This generates a 64-bit base 10 numeric ID. Okay. So it is basically a sequencer. It generates IDs in sequence like 1 2 3 4, but these IDs are 64-bit long, and these are base 10 IDs. What is meant by base 10 IDs? Base 10 IDs means it will use digits from 0 to 9. Okay. So it generates IDs in sequence. The IDs are 64-bit long, and these are base 10 IDs. So these IDs includes digit from 0 to 9. That is what our unique ID generator does. Okay. Ahead of unique ID generator, we have a base 58 encoder. What does base 58 encoder do? So it converts these 64-bit numeric IDs into alphanumeric IDs. Okay. Uh, what does this 58 mean? 58 represents the number of letters or digits we use in this encoder. So what all digits or alphabets do we use here? We use capital A to Z, small a to Z, and 2 to 9. So in this it excludes 0 and O, it excludes capital I and small l. So by this exclusion has been done to eliminate similar looking characters, Eliminating similar looking characters helps us improve the readability and reduces errors while typing manually. So that is why it is a base 58 encoder. Okay. So this base 58 encoder basically converts this numeric ID into alphanumeric ID. And once we have alphanumeric ID, we have a shortened URL. Okay. So this is what our shortening service does. Now let's see the redirection service. Redirection service is fairly simple. When we get a shortened URL, we check if the shortened URL exists in our database or not. What I mean to say is, if there is some long URL corresponding to which there is this particular short URL. So if it exists in our database, it will simply return the corresponding long URL. And if it doesn't exist in our database, then the URL redirection will fail. This is how the redirection service works. Now the point to be noted here is that while in the shortening service, we are looking for long URL in our database. We are searching for long URL in our database. In redirection service, we are searching for short URL in our database. So this creates an ambiguity. Which amongst these should be the primary key or the primary index for our database? Let's see. So we need to decide which of these is going to be used the most, or which of these is going to be indexed the most. Since our system is read heavy, we'll be getting more of redirection service, more of requests from redirection service. Now redirection service would be looking for short URLs a lot more, right? So in comparison, if we see short URL lookup is going to be a lot more in comparison to long URL lookup. So that for this reason, we'll choose short URL as the primary key or the primary index of our database. But there are also going to be significant number of lookup for long URLs in our database. And if there is no indexing put upon the long URL, long URL lookup will take significant amount of time, and we don't want that delay. So how do we solve that problem? We create a secondary index on long URL. Okay. Now let's understand this primary index and secondary index in context of MongoDB. So in MongoDB, whenever we create a collection, there is an ID field which is automatically indexed. Okay, and this ID field must be unique. So we can use this short URL code directly as ID. Okay, so doing this gives us order of one lookup for short URL. So this ID field's value would be the actual short URL, the URL that is shortened. So this is how the shortened URL becomes the primary index. Okay. Now we need to support idempotent shortening. Idempotent shortening means long URL should be unique and it should be shortened only once. So we need to create a unique index on shortened URL, on long URL. Okay. What is unique index and what does it do? A unique index enforces uniqueness constraint on the field, on the indexed field. That is, it enforces a uniqueness constraint on long URL. This means that no two documents in collection will have same value for long URL. So creating a unique index on long URL ensures that there are no duplicate long URLs. There is only one short URL per long URL, and it allows efficient reverse lookup. That is, it allows efficient lookup for long URLs that are going to be converted into, that are going to be checked against the short URLs. So it allows efficient reverse lookup. This is how we solve the problem of indexing, what should be indexed. Okay. Then the third service we saw is deletion service. It is again fairly simple service. Deletion service could be triggered on two occasions. A user might request to delete a shortened URL. So if the shortened URL exists in our system, we can simply go and delete that record. Deletion service could also be triggered when the shortened URL's time expires. How do we determine if the time for shortened URL has expired? We discussed that after some default amount of time we need to delete the shortened URL. So we can maintain one more field apart from long URL and corresponding short URL. We can maintain time to live. When this time to live field expires, we'll simply delete the that particular shortened URL. So that is how a deletion service would work. Then we also discussed that we need to support custom URLs. This is also a fairly simple job. For custom URLs, we can put some constraint like the URL, there should be some minimum length to this URL, let's say 11. It could be anything based on use case. And there would be certain allowed characters. So the base 58 encoder that we used, it uses 58 characters only, right? So we'll allow these 58 characters only for the custom short URLs also. Okay? So within these constraints, whatever custom short URL the user gives, if there is no duplicate URL in the system, we can allow that shortened URL, else we can deny. So that is how the high level design of our URL shortening service look like. Okay, now let's dive deeper into our high level design and let's see what problems it can have. The very first problem is that as the data storage requirement grows, MongoDB will shard our data into partitions. Basically it will create partitions. So with partitioning or sharding data, the problem is that how would application server know which database is present where? To solve this problem, we typically use consistent hashing. We deploy consistent hashing externally so that the partitions or the app server knows which data is present on what partition. But in this case, we don't need to deploy consistent hashing. Why? It is because we are using a distributed MongoDB setup, and in case of this setup, there is something called as Mongoose. What is Mongoose? It is an internal router. Okay. So MongoDB basically splits data based on shard keys, and Mongoose knows which shard has what range or hash of keys. Okay. So Mongoose knows which key is present on which shard. Hence, it is able to route query to the correct shard, and there is no need of external distribution logic or consistent hashing. So Mongoose does the job. We don't need consistent hashing to be deployed externally. Now, how do we ensure availability? What happens if a node goes down? Again, since we are using a distributed MongoDB cluster in this kind of setup, each node or each shard in a distributed MongoDB cluster is a replica set. What is meant by replica set? Each shard will have primary and secondary nodes, and each of them will contain same data. And when the primary node goes down, the leader election algorithm will kick in, and it will select a new leader. So that is what happens when a primary goes down. When secondary goes down, it is not a problem. There are multiple secondaries. Write request always goes through the primary node, and read request can be serviced by the secondaries as well. So if a node goes down and if it is a primary node, leader election algorithm will kick in. If it is not a primary node, if it is secondary node, other secondary nodes can do the job. So that is how we ensure availability in distributed MongoDB cluster setup. Okay. Okay. Now there is another problem. We had discussed that in order to generate shortened URL, we have unique ID generator that generates 64-bit base 10 numeric IDs, which is then fed to base 58 encoder. But this unique ID generator is basically a sequencer. It generates IDs in sequence. Okay? But the problem with sequential IDs is these IDs are susceptible to attacks, as it's very easy to predict what next ID would be. So this makes our system very easily scrapable and easy to reverse engineer. We don't want that. So what do? we need to introduce some mechanism in between that converts this sequential ID into some non-sequential IDs. We basically need to introduce non-sequentialness in our system between these two components. So how can we generate these non-sequential looking IDs? We need some transformation, okay? But we need to ensure that this transformation is a bijective transformation. What does bijective transformation mean? Each input maps to a unique output and every output maps back to exactly one input. Why is it required? It is required to ensure there is no duplication and you can easily map back to the original ID generated. So in order to have this, in order to enforce this, we need a bijective transformation. Okay, now what all techniques can be used for this bijective transformation? We can XOR the numeric ID being generated with a secret key. We can use AES encryption on the numeric ID, or we can also use Fistel cipher. So all these transformations are bijective transformation, and all this transformation will create non-sequentialness. Okay, so that is how we generate non-sequential IDs. Okay, now what happens if the sequencer goes down, the unique ID generator? What if it goes down? So we don't actually use a single node that is doing this job of creating sequential IDs. Instead, we use a distributed sequence generator like Twitter Snowflake. This ensures availability. This is a separate topic of discussion, and we'll not be covering how do we design a distributed sequence generator in this particular video. But there would be another video on this particular topic, and I'll put the link of this particular thing in the description. Okay, so I'll link the video in which I'll be discussing how to design a distributed sequence generator. So for now you can understand that we are using a distributed sequence generator, and distributed sequence generator will ensure availability. Apart from the unique ID generator, we also have a component that does base 58 encoding. What if that component goes down? So it is a simple component. We can have multiple nodes running this particular thing. If it goes down, there would be another node which can still serve a base 58 encoding. Okay, so that is pretty much it. I hope you would have understood this. Thank you.